Section 4.1, the product rule and power rules for exponents. So we're really changing gears from what we've been doing in Chapter 3. We're now going to take a look at the rules of exponents. Remember that when I have something raised to a power, we call this little guy the power or the exponent. This is the base. The base is raised to that power. And by definition, this is repeated multiplication. 2 raised to the third power, or 2 cubed, is 2 times itself 3 times. Now, you've got to be careful when it comes to signed numbers. Let's think about this. If I have 5 squared, 5 to the second power, that means 5 times 5, which is 25. If I have a negative 5 squared, what's being squared? What is the base of this exponent? What this really is a negative 1 times that 5 squared. And so this negative out front is just floating. Order of operations says the power takes place before the multiplication. So this negative 1 is not participating in that power. He's waiting on the power to get finished. And so this negative is simply going to float into the next step. 5 squared is 5 times 5. And so this is negative 25. Compare that to negative 5 squared. Now what's the base of the exponent? Now what's being squared? The whole negative 5, the whole thing. So what's being multiplied times itself? The negative 5. And this will give me a positive 25. So watch very carefully on those signs. If there are no parentheses, that negative's just floating. Let's go ahead and look at a couple of homework problems. Number 10. Number 10 says to write each expression in exponential form. We have a negative 3 being multiplied times itself 6 times. So this is going to be that negative 3 to the 6th power, but careful, this would be wrong, because this is not raising negative 3 to the 6th power. This is 3 to the 6th power with a negative out in front. How do I make that negative 3 the base? Put it in parentheses. Negative 3 quantity to that 6th power. Look at number 14. She says, explain how these two expressions differ. The quantity, 5x to the third power, and 5x to the third. In this first expression, what is the base? What's being cubed? It is the whole 5x. So this is 5x times itself 3 times. Compared to this expression, that 5 is just floating out front. A power outranks multiplication in the order of operations, and so that power is attached only to the x, and that 5 would be waiting around. For example, if we plugged in something for x, we would raise it to that power and then multiply by 5. So how could I express this in an expanded form? It's that 5 times 3 factors of x, because what's being cubed? Just the x. We have 4 rules that we want to develop in this section. And so let's spend some time now developing these rules. Consider, if I have some number a, raised to the second power times that same a to the third power. Can I simplify? Can this be simplified further? Well, order of operations would require me to take the powers before I multiply. Is there any way the algebra can let me around that? Well, by definition, a squared is 2 factors of a. And a cubed is 3 more factors of a. Strictly speaking, I would have parentheses like this. But what do I know about multiplication? Multiplication is associative. And so I can drop those parentheses. What do I have? 5 factors of a, which by definition is a to the 5th power. Now look at the top, look at the bottom. What appears to have happened to my powers when I multiplied these like bases? It looks like we added 2 plus 3 is 5, and that's exactly what we did, because we're counting up how many total factors of a there are in this expression. There are a total of 5 factors of a to the 5th. And so this leads us to our first rule. Brown box, page 263, says for any positive integers m and n. So these are for positive powers. It says a to the m times a to the n equals a to the m plus n. All that says is that if I have a product of like bases, I will add the exponents. If I'm multiplying, if I have a product of, if I'm multiplying like bases, then I can add those exponents. And that makes sense to us because what are we doing? We're counting up how many factors. I don't want you to just memorize these brown boxes. I don't want you just to memorize the rules. I want you to understand where they come from. Because if you understand why they work the way they do, then getting them to work how they do is no problem. And remembering the rules becomes much easier. The next rule we're going to develop, let me start with something that looks like this. B raised to the 2nd power, all raised to the 4th power. Is there any way I can simplify this expression? Well, let's go back to our definition of exponent. Something to the 4th is that thing times itself 4 times. And each one of these b squareds is just b times b. And so if I count them up, I see that what I really have, because multiplication is associative, all I really have is 8 factors of b. And collapsing this back down using that definition of exponent, this will be b to the 8th power. What does it appear has happened from top to bottom? It looks like we multiplied those powers. Well, of course we did. Because this says what? I have 4 groups of 2 each. Right here in the middle, 4 groups of 2 each. Isn't that when you multiply? When you have 4 groups of 2 each, that's 4 times 2, that's 8 total things. And so it makes sense that when I have a power to a power, we multiply those powers. This is shown in the brown box middle of page 264. Your book calls this power rule A. You'll typically hear me call it power to a power. Power to a power. And it says, if I have a to the m to the n, that's just a to the m times n. That is, if you have a power to a power, you multiply the powers. So there's our second rule. To develop our third rule, let me look at a situation like this. I have a product raised to a power. Is there any way I can simplify this? Is there any way I can remove the parentheses from this expression? Well, by definition of exponent, this is 3 factors of this product. Multiplication is commutative and associative. So I can group however I want, associative property. I can put them in any order that I want, commutative property. Well, the associative property then lets me drop all of these parentheses. The commutative property lets me put these in any order that I want. Let me gather the C's together and gather the D's together. And while I'm at it, go ahead and regroup. Multiplication is still associative. I can group it however I want. By definition of exponent, this first thing in parentheses is just C to the 3rd power. Likewise, D to the 3rd power. Now look from top to bottom. What does it appear has happened with my exponent? It looks to me like we distributed that exponent. We distributed that exponent over this multiplication. A lot of teachers don't like calling this a distributive property because they are concerned that you are going to misremember and you're going to have something like this: x plus y quantity squared, and you're going to write x squared plus y squared, when that's not what happens at all. These two things are not equal to each other. We'll find out later in chapter 4 that this is equal to x plus y times x plus y, and if you remember from your high school algebra, we'll FOIL that out. But do not distribute a power over addition or subtraction. Do not distribute a power over addition or subtraction. She even gives you a word of warning here, the caution, in the middle of page 265. She warns you not to distribute a power over addition. I consider that to be an unforgivable mistake. An unforgivable mistake. But you can distribute a power over multiplication. And so we have our brown box at the bottom of page 264. A product, a times b raised to some power m, is equal to a to the m, b to the m. That is, we can distribute a power over multiplication. Now, think back. Our distributive property, it allows us to distribute multiplication over addition, right? Our distributive property allows us to distribute multiplication also over subtraction, because subtraction is just adding the opposite. It still behaves like addition. We can distribute multiplication over addition. We can distribute multiplication over subtraction. Multiplication is repeated addition. A power is repeated multiplication. A power can be distributed over multiplication. Wouldn't you expect then that a power can be distributed over division? So let's consider. Can I simplify this? Can I remove those parentheses? Well, by definition of power, this is 4 factors of this fraction. To multiply fractions, you multiply the tops, multiply the bottoms. And what do I end up with? 4 factors of g, which is g to the 4th, over 4 factors of h, h to the 4th. And from top to bottom, what does it appear has happened? It looks like I've distributed that power of 4 over that division. I've distributed that power to the top and bottom of that fraction. And so our fourth rule we find on page 265, just below the center. If we have some fraction, some division raised to a power, that is going to be the same as the numerator to that power over the denominator to that power. In other words, it looks like I'm distributing. So, your book calls this Power Rule C, and the previous one Power Rule B. I'm going to call them both distributive properties, because that's what we're doing. Just remember, you cannot distribute a power over addition or subtraction. And I consider that to be an unforgivable mistake, especially by the time we're done with sections 4.5 and 4.6. So if you look on page 266, we have a brown box that summarizes the rules that we have so far. Our product rule, which tells us that product of like bases, you add the exponents. Our power rules. What she calls power rule A, I call power to a power. When you have a power to a power, you multiply the powers. And the last two, those are our distributive properties of powers. It says you can distribute a power over multiplication. You can distribute a power over division. Make sure you understand where these rules come from. It is important to understand where the rules come from so that they make sense when you go to use them. Let's jump back into the homework now. Number 16. Number 16. 2 to the 7th. And she asks us to identify the base and the exponent of each of these expressions. The base, what's being raised to the power? The base here is 2, and the exponent is that 7. Number 18. Parenthesis, -2, raised to the 7th power. What's the base? What's being raised to that power? That whole -2. And the power, of course, is that 7. Number 20, in parenthesis, -8x, all to the 4th. What's the base? What's being raised to that 4th power? That whole -8x. The exponent is the 4. Number 22, -8x to the 4th. No parentheses. What is the base? What is the only thing that's being raised to a power here? Just that x. That -8's floating out front. And the power on x is 4. It is absolutely vital that you be able to identify the base in an exponential expression, because that's the only way you're going to know what's actually being raised to that power. Let's look at number 26. Now, let's look at the instructions very carefully. It says, use the product rule for exponents to simplify each expression if possible. Write each answer in exponential form. Write each answer in exponential form. So when I work this one, we're not being asked to crank this out completely and get some ridiculously large number. We're just simply being asked to deal with the exponent. Simplify it exponentially, and specifically using the product rule. A product of like bases, you add the exponents. And that's what we have here. A product of like bases. So we add the exponents. This will be 3 to the 6 plus 7, 3 to the 13th power. And if you picture this in your head expanded, you've got 6 factors of 3 times 7 more factors of 3. What do you have? 13 factors of 3. And she said leave it in exponential form. Number 34. We know that multiplication is commutative and associative. The associative property lets me drop the parentheses. The commutative property lets me reorder the factors. And so, at least in my head, and this is probably just a mental step, I don't know that we'd actually need to see this on our paper, but what we're going to do, at least in our head, is drop the parentheses, get my numeric factors together, get my exponential factors together, so that I'm going to be saying 10 times negative 4. 10 times negative 4 is negative 40. And a to the 7th times a to the 3rd. Product of like bases, add the exponents. How many a's are there altogether? There are 10 total factors of a. Product of like bases, add the exponents. And that's what she's after. In number 40, now because of the way the instructions are written, she says use the product rule to simplify if possible. Does the product rule apply to this problem? Is this a product of like bases? No, this is a sum. We're adding, we're not multiplying. So, the product rule does not apply. And I believe she says something similar in the back. This will never be the answer on a quiz or a test. If I were to give you something like this, first of all, I'd make those powers much smaller, and I'd be testing you on your order of operations. I'd expect you to crank it out. But because of the way the instructions are written here, she just said, use the product rule if possible. Well, the product rule does not apply to this because it's not a product. Number 42. Because the instructions say, use the product rule if possible. And we look at this and we say, well, the product rule does not address this. This has nothing to do with the product rule. The product rule, this is a product, but do the bases match? Is this a product of like bases? No. So the product rule does not apply. Like I said, if this were on a quiz or a test, first of all, your powers, well, especially that 9, would be much smaller, and I'd expect you to crank it out. Because all I would say is simplify. But she's wanting to look specifically at the product rule in these cases and make sure you know when not to try to add those powers. When you have a product of like bases, then you can add the exponents. Number 46. Y to the 6th to the 5th. The instructions say use the power rules for exponents to simplify. Assume that variables and denominators are not zero, so we know we're not going to run into any kind of undefined situation. And again, it says write each answer in exponential form. We don't actually have to raise numbers to powers. We're to leave it in exponential form. So, what rule applies here? Your book calls it product rule A. I'm sorry. Your book calls it power rule A. Power rule A. I call this power to a power because that's exactly what it is. And when you have a power to a power, what do? You multiply those exponents. We have 5 groups of 6 each. That's 30 total factors of y, right? Make sure you understand where the rules come from. Number 50. This is going to be our distributive property over multiplication. Your book calls this power rule B. I call it distributing a power. I can distribute this power to each of the 3 factors inside the parentheses because they are factors. They're being multiplied together. You can distribute a power over multiplication. 9 to the 6th, p to the 6th, q to the 6th. And she said leave it in exponential form. Strictly speaking, if you were asked to simplify, you would be expected to figure out what is 9 to the 6th power. Again, I would give you numbers much smaller and easier to deal with if I were asking you to fully simplify. Number 56. In number 56, we're asked to simplify but leave our answer in exponential form. So what applies here? Is there some way I can remove these parentheses, which is part of simplifying? I can distribute this power because that's a multiplication inside, and you can distribute a power over multiplication. The 4 is not participating. The 4 is not part of the base. The 4 is just out front floating. So we have 4 times, and now what's going on over here? V to the 5th, W to the 5th. But the 4 remains unaffected because it was not in the parentheses, it was not participating as part of that base. Number 62. We're asked to simplify, leaving our answer in exponential form. Is there a way to remove those parentheses? Well, power rule C, which I just called distributing, says we can distribute this power over division. We can distribute that power to the top and bottom of that fraction. R to the 4th over T to the 4th. I want to compare this to number 64, and I want to compare her instructions right now to what my instructions might be on a quiz or a test. Her instructions said simplify, leave your answer in exponential form. Well, this is essentially the same as the last problem. We're going to distribute this power to the top and bottom of our fraction. Y to the 4th over 3 to the 4th. And because she said leave your answer in exponential form, we can leave that 3 to the 4th power. However, on a quiz or a test, I'm very likely just to say simplify. In which case, not only would you need to drop the parentheses as we've done here, but you would need to keep going. If all I say is simplify, you've got to crank this out completely. Can't do anything else with y to the 4th, but 3 to the 4th power, 3 times 3 times 3 times 3, isn't that 9 times 9, which is 81? So if I ask you to simplify, I need it finished. I need it finished completely. Which brings us to this next batch of homework problems, starting with number 67. And I do have a little issue with your textbook at this point. The instructions. We're going to grab number 70. The instructions say simplify each expression. Simplify each expression. And for a problem like this, I wish she had just given letters. A over B, quantity to the 4th times A to the 3rd would have been better, I think, because when she works this, the instructions say simplify. Well, we're going to drop the parentheses by distributing that 4, top and bottom, 8 to the 4th, over 5 to the 4th. We're going to keep going. We know that this factor can be thought of as over 1. Multiply the tops, multiply the bottoms. When you multiply the tops, 8 to the 4th times 8 to the 3rd, that's a product of like bases. So we add the exponents. 8 to the 7th over our 5 to the 4th. And she stops. You look this up in the back of the book, and that's where she stops. And I have to disagree with that. I have to disagree with that, because it is possible to continue this further. This denominator would be 625, and I'm not even going to bother to think about what 8 to the 7th power is. I don't care. The thing is, on a quiz or a test, if I say simplify, I will give you much smaller numbers to work with. But if you have numbers, you've got to crank them out. So we're going to have to take this part of the homework with a grain of salt. A lot of these you'll look up in the back, and they're going to turn out to be what we would not consider simplified. But the goal right now is to get used to using these rules. So I might say that for these problems, you could follow the instructions: simplify, leaving your answer in exponential form. Okay? So that's how we'll fix this. When you're working on problems 67 through 83, assume that the instructions say simplify, leaving your answers in exponential form. Let's do another one. Number 78. Of course, what we're doing in this bank of problems is putting all of these rules together. Simplify. Now this one doesn't have any numbers raised to a power, so the instructions simplify work just fine here. What are we going to do first? Before we can get these bases together, we've got to get them out from under parentheses. To remove this first set of parentheses, this is a power to a power. When I have a power to a power, I multiply those exponents, y to the 20th, times, again, power to a power. Multiply the exponents. 3 times 5 is 15. And then the only thing left to do is multiply. This is a product of like bases. A product of like bases, you add the exponents. Y to the 35th power. Let's try number 80. All right, hang on. Here we go. First thing I need to do is drop the parentheses. I have a product to a power. My product has 4 factors, so I'll have 4 little rainbows to indicate that distribution. I'm going to distribute this power to every factor in that product. So we will have 3 to the 3rd power. Now stay with me here. X to the 4th to the 3rd. There's another rule. That's a power to a power. As I distribute this 3 in on my factors of x, I have x to the 4th to the 3rd, power to a power, you multiply x to the 12th. Same thing here. This is y squared to the 3rd, power to a power, you multiply. And this, of course, is just z to the 3rd. We'll distribute this power in on the 2 factors in this second set of parentheses. That's going to give me y to the 5th and what? Z to the 4th to the 5th. That's a power to a power. So we multiply those powers. Let's finish this one up. Now here's one. You look it up in the back of the book because she's decided to go ahead and say 3 cubed is 27. Like I said, we are not going to get too bent out of shape in this section. I think the instructions should have been worded a little differently, or the problems written a little differently, answered a little differently in the back. But we're not going to get too bent out of shape right now. If on a quiz, all I say is simplify, you absolutely have to say 3 cubed, 3 times 3 times 3 is 27. We've got an x to the 12th. We have here a product of like bases. Y to the 6th times y to the 5th is y to the 11th. Product of like bases, add the exponents. Same with the z's. Z is to the 23rd power as I add those exponents. And this answer is simplified because we did raise that 3 to the 3rd power. Number 82. Similar to the previous problem. We've got some negatives running around, and those negatives are participating as part of the base in each case. As I go to distribute my power in on these products, I want to think about this negative as a factor of -1. You can't see the 1, but I want to think of it as a factor of -1. So we're going to raise this negative to the 4th power, and raise the t to the 4th power, and raise the s to the 6th to the 4th power. -1 times itself 4 times. That would be 4 negatives. Does that turn out positive or negative? -1 times -1 times -1 times -1. Every pair of negatives makes a positive. So if I have a negative raised to an even power, it's going to give me a positive 1 that I would not typically write. T to the 4th, well, that's what we've got there. And s to the 6th to the 4th, power to a power, you multiply the powers to get s to the 24th. Now, thinking of a -1 sitting out front here, I'm going to distribute that power on the outside to each of these 3 factors. -1, the whole thing, a negative cubed, a negative to an odd power. -1 times -1 times -1. Every pair of negatives makes a positive. I've got 1 left over. So this is going to be -1. -1 to the 3rd power is -1. I would not typically write that 1. I would grab me some parentheses so that my dot and my negative don't bump into each other, or if I chose not to write a dot, it's not going to look like subtraction. And then t to the 3rd multiply t to the 9th, s to the 5th to the 3rd, s to the 15th. Let's do that step again, except this time I'm not going to show the 1s. Simplify. To drop this first set of parentheses, I'm going to bring this power of 4 in on the negative as well as the t and s factors. A negative to an even power is positive, so I don't have anything to write. T to the 4th, well, that's t to the 4th. S to the 6 to the 4th is S to the 24th. Times a negative to an odd power as I distribute. A negative to an odd power is still negative. T to the 3rd is T to the 9th. S to the 5th to the 3rd, S to the 15th. This is how I would typically show that step. We don't have to see those ones. If they help you out at this point, go ahead and put them. Be sure that they do not show up in the final answer, because 1 times something is just itself, and so that would not be simplified. Let's finish this off. We know that multiplication is associative, so I can drop those parentheses, at least mentally. I have a positive times a negative is negative. T to the 4th times T to the 9th. Product of like bases, add the exponents. T to the 13th. And my S's, product of like bases, add the exponents. 24 plus 15 totals 39. Watch your signs very carefully. Watch your signs very carefully. Number 84. Power rule C says that I can distribute a power to the top and bottom of a fraction. That would look like this. I would have that numerator, all raised to the 4th power, over that original denominator, all raised to the 4th power. Then what am I going to do? I'm going to turn around and distribute this 4 over that product. Knowing that that's going to happen, and that's how it will work every time, here's what I typically show. We know that we can distribute a power over multiplication and division. Power rules B and C. I call them distributing. I can distribute this power 4 to every factor on the top and to every factor on the bottom. And so this is going to give me 6 to the 4th, x cubed to the 4th. Power to a power, you multiply x to the 12th. Y to the 9th to the 4th, multiply y to the 36th. And z to the 5th to the 4th, power to a power, we multiply z to the 20th. And like I said, assume that the rules say simplify, leaving your answer in exponential form. And we'll just go with that for now. I find it interesting. You turn to the back of the book, and on this one she says, or 6 to the 4th turns out to be 1,296. She says, or you can write your answer this way. Still my favorite textbook author, but this is one place. This is one place where I don't wholeheartedly agree with what she's done here. If I say simplify, only this last answer is correct. If I say simplify, leaving in exponential form, only this first answer is correct. So again, we're going to make sure that we've got our laws of exponents down and not worry too much in this set of the homework from 67 to 83 about the way the instructions are written. Let's do a couple of these geometry problems. Number 88. We're given a triangle whose base measures 4m to the 4th, and whose height, the height of a triangle, is found by dropping a perpendicular from one vertex to the opposite side. Drop a perpendicular, and the height of this triangle is m squared. And we have been asked to find an expression that represents the area of the figure. Find the area. Find the area. That's all I would say. Find the area. And I would give you that figure. Well, we need to know our formulas, don't we? The area of a triangle is 1/2 its base times its height. 1/2 the base times the height. So we plug in 1/2 times the base is 4m to the 4th times the height is m squared. 1/2 times 4, half of 4 is 2. M to the 4th times m to the 2nd, product of like bases, add the exponents. M to the 6th power. I'm going to tell you right now, I like these problems. These are good problems. Number 92. Number 92, we're given a rectangular solid and asked to find its volume. This is not one of those formulas that I have asked you to memorize for this semester, but I can only imagine if you've been to high school, you know the volume of a rectangular solid is its length times its width times its height. We are given 5x cubed y on that edge. This edge measures 9xy cubed. And what I would probably call the height here, 4x squared y to the 4th. Length, width, and height are all interchangeable. It doesn't matter which one you call what. Okay? The length is not the longest side. The height is not necessarily from the ground up, because I could turn this on its side and then that would be interpreted differently. The length, the width, and the height, they're all interchangeable. I think most of us would call the length that 9xy cubed. And I bet most of us would refer to the 5x cubed y as the width and the 4x squared y to the 4th as the height. But you know that multiplication is commutative, so it really doesn't matter what order we end up putting those in. In our head, we're going to drop the parentheses because multiplication is also associative. And we're going to multiply. I think the easiest way to deal with our numbers is to say 5 times 4 is 20 times 9. 5 times 4 is 20, and 20 times 9 is 180. Now let's gather up the x's. This is a product of like bases, so I'm going to add the exponents. Remember, I've dropped the parentheses, at least mentally. So I'm going to gather my x's together. Product of like bases, add the exponents. This x is being raised to what power? This x by itself has what power on it that you cannot see? That's x to the first power. That's a single factor of x. In other words, x to the first power means one factor of x. So an x by itself is x to the first power. 1 plus 3 plus 2, x to the 6th. We're just counting up how many factors of x there are total in that product. That's why that rule works the way it does. And y to the 3rd times y to the 4th. Product of like bases. Add the exponents. We understand that a y by itself is y to the first power. And so we have 3 plus 1 plus 4, a total of 8 factors of y in that product. And so here's an expression that represents the volume of the given rectangular solid. If you look ahead in the next section, we have many more rules of exponents that we're going to explore. And we're going to take 2 days to do the next section. There's a lot going on in the next section. We've got to have section 4.1 down pat before we go into section 4.2. So I will let you get started on that.